Amid the majestic Alps, where lakes hang suspended thousands of meters above sea level, Swiss engineers have carried out one of the boldest feats in hydropower, building massive dams to raise water levels by tens of meters and drilling straight through mountains to connect two reservoirs separated by an entire mountain range. Behind this achievement is not just concrete and steel, but a true battle against extreme terrain. Blasting rock at elevations close to 2,500 meters, transporting materials along thread-thin mountain roads, and excavating kilometer-long tunnels through solid rock to create an energy artery between the two lakes. Thousands of engineers, workers, and giant machines have transformed a remote alpine landscape into a hydropower system capable of storing and releasing energy on demand. So how do you build a massive dam halfway up a mountain and tunnel through the Alps to link two lakes together? Let's explore with Mandarin Tech. The Limmern Pumped Storage Hydropower Plant is located in the Linthal Valley of Switzerland, with two core components, the Mutsi Dam and a network of mountain tunnels housing an underground power station. Lake Mutsi, situated at an elevation of over 2,400 meters, has been upgraded with a massive concrete dam capable of holding water up to 35 meters deep, with a base thickness of about 25 meters, making it the highest reservoir in Europe. Below it lies Lake Limmernboden, around 630 meters lower, creating a significant elevation difference that acts as a natural energy battery. To connect the two reservoirs, engineers excavated several kilometers of tunnels through solid rock, forming a high-pressure water conveyance system. Construction began in 2008 and was completed in 2016, with a total investment of over $2.3 billion. More than 1,000 engineers and workers operated continuously at altitudes near 2,500 meters, transforming an entire mountain range into a massive energy storage system. Switzerland's major energy company, Axpo, launched to construct a new dam at Lake Mutsi in order to expand its water storage capacity. Initially, the reservoir held only about 9 million cubic meters, far too small to efficiently operate a large-scale pumped storage hydropower system. The solution was to increase the capacity to over 25 million cubic meters by building an entirely new dam. The dam stretches over 1 kilometer in length and was constructed during 3 consecutive summer seasons from 2012 to 2014. A narrow window each year when weather conditions at nearly 2,500 meters. Due to the terrain not being steep enough for an arch dam design, engineers opted for a gravity dam with a triangular cross-section. Its base extends to roughly 25 meters wide. It's relying on its immense mass to remain stable and withstand water pressure reaching depths of up to 35 meters. However, this design also created a massive material challenge. Transporting millions of tons of concrete and equipment to a construction site at an altitude of nearly 2,500 meters became an extremely complex logistical operation. Most of the dam was constructed using material excavated from tunnels and underground caverns during the construction process. All of this material was transported up the mountain via a dedicated construction cable car system and then stockpiled at intermediate staging areas. The transport operation alone required more than 20,000 cable car trips, highlighting the enormous logistical scale of the project. From these staging areas, the material was sent to a processing plant where it was crushed into standardized sizes and sorted before being stored. The gravel and aggregates were then delivered to a concrete plant, where different concrete mixes were automatically produced according to specific requirements. Thanks to this system, a constant supply of concrete was maintained, ensuring uninterrupted progress in the dam's construction. Large dump trucks continuously delivered aggregates into mixing hoppers, where they were processed into concrete directly on the high-altitude site. The concrete was then loaded into heavy containers and lifted by cranes to precise positions along the dam. Massive cranes, dense scaffolding, and workers operating amid fog and snow created a harsh yet constantly active construction environment. The dam was constructed from 68 separate blocks, each about 15 meters wide. At first, engineers used a staggered sequence, building every second block first, and the walls of these blocks then acted as formwork for the next ones. Recessed features on both sides allowed the blocks to interlock and lock tightly together. Before construction, the site was excavated about 2 meters down to solid bedrock. The entire foundation was precisely surveyed, measured, and mapped by geologists. Cracks and fault zones in the ground were treated with specialized concrete to ensure stability. The blocks were built in stages, each 3 meters high. The formwork for the lowest layer was carefully aligned according to the design. Concrete was transported by dump trucks to the site and lifted into the formwork by crawler cranes. And as each full bucket could weigh up to 17 tons, requiring the crane to operate close to the dam block. At the base of the larger sections, cooling pipes were installed to prevent excessive heat during curing, reducing the risk of cracking. Each 3-meter section was divided into 6 layers, each about 50 centimeters thick. After pouring, the concrete began to set immediately, so it had to be quickly leveled and compacted using vibrators. The schedule was extremely tight. Each new layer had to be poured within a maximum of 2 hours to ensure proper bonding. Even with continuous high-speed work, completing one large concrete section could still take up to 12 hours. After each concrete layer was completed, its surface was roughened using high-pressure water to create maximum adhesion, allowing the next layer to bond tightly as a single unified mass. At the same time, an inspection gallery was built inside the dam, running throughout its structure and acting like a nervous system, where engineers can monitor, measure, and maintain the entire structure throughout its operational life. The highest blocks of the dam reached the height of a 10-story building and were constructed in 12 stages. At the top of the dam, the layers become extremely narrow, leaving almost no space for construction equipment to operate. Under these conditions, crane operators cannot even see the multi-ton concrete buckets and must rely entirely on radio guidance to position them. Nearby, machines and workers coordinate continuously in tight spaces, where each layer of concrete must be handled precisely within a very short time before it sets. Just before completing a construction phase, fog suddenly rolled in, making visibility much more difficult. The site is located in a high mountain area at around 2,500 meters, where the weather remains unpredictable even in summer. No one can know exactly when snow will arrive in autumn and force construction to stop. For this reason, the site never shuts down at night. Operations continue 24 hours a day, while crawler excavators place concrete into formwork on the lower blocks. Climbing formwork systems are being prepared on the upper sections for the next pouring stage. In the darkness, unfinished blocks stand like massive concrete structures rising from the Rocky Mountains. In 2013, favorable weather conditions allowed construction to make impressive progress from spring through autumn. In November, the final concrete phases of the year are completed against a stunning winter backdrop. Before the harsh winter fully sets in, the main body of the dam is finished on schedule as planned. The remaining sections of the dam are constructed in 2014, and by 2015, the dam crest is officially completed. At that point, it becomes the longest dam in Switzerland, far surpassing all others. By 2016, the reservoir was filled for the first time. The massive volume of water stored behind the dam was then ready to be used for peak time power generation, providing flexible energy for Switzerland's entire electricity system. In addition to building the dam, engineers excavated a tunnel system about 4 to 5 kilometers long through the mountain to directly connect the two reservoirs, while also placing an underground power plant deep inside the rock. The two reservoirs have an elevation difference of around 650 meters, allowing water to flow between higher and lower levels to generate electricity during peak demand. The entire system was constructed in hard rock using highly complex drilling, blasting, and advanced tunneling technologies. To allow the tunnel boring equipment to advance into the mountain, the first step is to drill a series of deep holes into the rock using specialized drilling machines. Engineers then place carefully calculated amounts of explosives into these holes, connecting them with a detonation system designed to trigger in sequence. When the charges are detonated, the rock is fractured, creating an opening that allows the tunnel to progress deeper into the mountain. They continued blasting deeper into the mountain, and the further they advanced, the harsher the working conditions became. with increasing rock pressure and limited working space. This is the massive cavern inside the mountain, measuring up to 125 meters long, 35 meters high, and 25 meters wide, constructed using a top-down rock excavation method. Each blast used up to 800 kilograms of explosives, breaking about 1,500 cubic meters of rock. All the rock blasted from the mountain had to be transported out continuously and under strict control. Just below the underground caverns, a separate tunnel was built to crush the rock on site, reducing its size and optimizing transportation in the confined space. Most of the material was then transported up the mountain to support the construction of the Mutsi Dam, making full use of resources available directly at the site. The remaining portion was sent to an underground concrete plant, where it was processed and recycled into concrete, which was then reused to reinforce and complete the underground structures. As the work progressed deeper into the mountain, a major problem began to emerge. Groundwater from within the rock layers continuously seeped in, making the construction environment increasingly difficult and dangerous. At first, the water was under relatively low pressure, but after several blasting rounds, it suddenly surged out with pressures of up to 10 bar, equivalent to a water column about 100 meters high. According to the plan, there would be around 250 blasting cycles with more than 20,000 drilled holes for explosives. Although water kept seeping in, the pressure was initially low enough not to pose a serious threat, and specialized explosives still performed reliably in the wet conditions. However, in reality, the engineers had to stop and carry out geological probing, and the results showed that water continued to flow in at a high rate, up to 100 liters per second, indicating a serious challenge hidden deep within the mountain. To continue construction, they were forced to use a waterproofing solution by injecting materials into rock fractures to prevent water from flowing into the tunnel. The process began by sealing the end of the tunnel with a concrete plug to prevent the injected material from flowing back. Then, a series of boreholes were drilled to inject waterproofing materials into the water-bearing cracks. Initially, cement was used, which worked well for small fractures and low water flow. However, when encountering larger cracks with strong water flow, the cement was washed away, forcing them to switch to a hybrid technology, combining cement with polyurethane, PU resin, to increase density and sealing capability. This method allowed the material to block large fractures while also creating pressure that helped the cement penetrate smaller cracks behind them. In reality, every drilling operation had to deal with high-pressure water bursts. After installing 14 sealing layers with nearly 1,000 boreholes, the team successfully passed through the fractured, water-rich zone, an achievement that even engineering experts found remarkable. The construction team finally reached a stable rock layer. Soon after, they began building the launch platform for the tunnel boring machine. This platform was designed to position the machine at the pre-drilled tunnel entrance and establish an initial incline of about 26 degrees. An 80-meter-long horizontal chamber was prepared to assemble the TBM. The machine was transported to the site in 6 separate components, with the cutter head being the largest, and its size ultimately determined the diameter of the access tunnel. Transporting these massive components up the mountain was a major challenge for the truck drivers. The cutter head was lifted using a specialized hydraulic system, and once fully assembled, the entire machine reached a length of up to 100 meters. Even while the final components were still being installed inside the chamber, the tunneling process had already begun. After about 3 weeks of continuous adjustments and optimization, the entire machine was finally fully positioned inside the rock, and the tunneling process entered a stable operational phase. During operation, 23 cutter rollers on the cutter head rotate under extremely high pressure, crushing the rock into small fragments. The broken material then falls behind the cutter head and enters a dedicated transport channel. From there, the excavated rock automatically slides down along the inclined tunnel axis, while being mixed with water directly at the cutter head to facilitate transport. Thanks to the continuous cycle of excavation, advancing, and stabilization repeated day and night, after hundreds of days of uninterrupted construction, the tunnel gradually extended deeper into the mountain. In the end, the nearly 5-kilometer-long tunnel connecting the 2 reservoirs was completed, forming the core water conduit of the entire system. Then the project entered a new phase, transforming the raw tunnel into a high-pressure water conduit. Water from the upper reservoir is released to generate electricity, creating immense pressure on the tunnel walls due to the significant elevation difference. To withstand this force, the entire tunnel was reinforced with thick steel lining, acting like a protective armor. These steel sections were fabricated from plates about 6 centimeters thick at a dedicated facility, then transported into the tunnel and assembled into a complete water conveyance system. These pipe sections were first transported close to the construction site, then moved further using a construction cable crane system. Each steel pipe was handled with carefully calculated and precisely coordinated operations. The pipes were then lifted an additional 600 meters in elevation without interruption, temporarily stored near the tunnel entrance leading to the powerhouse cavern, before being moved inside for installation and further processing. The steel pipe sections were welded together to form larger segments, each about 9 meters long and weighing up to 60 tons, almost as heavy as a locomotive. These were then lowered into the tunnel using a specialized cable hoisting system. At a depth of nearly 600 meters, the installation area had already been prepared to connect each segment, forming a continuous water conveyance line. Working inside the shaft, which is inclined at around 40 degrees, was an extreme physical challenge, especially since all welds were carried out manually by top-level welders. Each weld could take 4 to 5 days to complete and was inspected multiple times. One of the key methods was magnetic testing, which reveals defects through characteristic surface patterns. Once approved, each pipe segment was finished with an anti-corrosion coating before being put into operation. And so, the tunnel system was completed, despite the considerable complexity of its construction. After that, the generating units were fully installed deep inside the mountain, directly connected to the high-pressure pipeline system. When the water level in the upper reservoir is high, water is released down through the pipes, and the powerful flow spins the turbines to generate electricity. Conversely, when demand is low, the system pumps water back up to the upper reservoir to store energy. Thanks to this mechanism, the plant can operate flexibly like a giant battery, both generating electricity and storing energy when needed. To connect the plant to the national grid, high-voltage cables were installed along the access tunnel, leading to the substation at Tierfed. From there, a new 380 kilovolt transmission line was built, stretching about 17 kilometers across the valley, supplying electricity to thousands of households in the surrounding area. So, you've learned about the entire process of building the dam and tunneling this magnificent power plant. If you enjoyed it, please continue watching our new content. Goodbye and see you in the next videos.